In this video, we're going to be looking at applications of linear systems. So we're going to solve 5 real-world problems by solving a system of equations. First problem we're going to look at, let's say we're given 3 points, and we want to find the equation of the parabola y equal ax squared plus bx plus c that contains those 3 points. So first thing we can do is write down that equation y equals ax squared plus bx plus c. And we're going to start with our first point, which was x equal 1, y equal negative 2, and we're just going to sub that into our equation. So subbing in, we'd have negative 2 equals, subbing in x equal 1 on the right side, we'd have a plus b plus c. So that gives us one piece of information about these unknown a, b, and c that we're trying to find. So in this problem, it's really the a, b, and c that we're solving for. And in a similar way, we'll sub in the coordinates of our other 2 points. We'll get 2 other pieces of information about a, b, and c, and then we can set up a system. So second point was x equal negative 1, y equal 8. So again, let's sub that in to the equation at the top of the screen here. We'd have 8 equals, well, when we square negative 1, we get a positive 1. So this looks like a minus b plus c. So that's our second equation. And then third equation is going to come from x equal 2, y equal negative 1. So subbing that in, we'd have negative 1 equals, well, when we square the 2, we're going to get 4. So it'd be 4a plus 2b plus c. So there we go. We've got our 3 equations involving a, b, and c. So let's put those into a matrix. So we got our variables a, b, c here. First equation translates as 1, 1, 1 equals negative 2. And in a similar way, we can write down our other 2 equations. So I'm just going to write a squiggle here. Imagine that we do some work and we get this matrix into our REF. Here's what the REF is going to look like. So you can go through and check that work if you like. Our A value is 2. So let's write this as an ordered triple, 2, negative 5, 1. And the way the question was worded, it was asking for the equation of the parabola. So we could say, well, the equation is y equal ax squared plus bx plus c. And if we just sub in our values into the appropriate places, here's our answer. Y equals 2x squared minus 5x plus 1 is the parabola that passes through those 3 points. So let's take a look at the second question here. NASA is planning a Mars mission, and their dietitians must design a food supplement that provides enough vitamin A, vitamin C, and calcium. Everything here is measured in milligrams. And there are 3 possible ingredients. We'll just call them ingredient 1, 2, 3. So they each have differing amounts of the vitamin A, C, and calcium. The question is it possible to design a supplement from these ingredients? If so, how much of each ingredient must be used? So typically with these word problems, if you look at the very last sentence, that usually gives you an indication. Often it gives you an indication of what your variables should be. What do we really care about? How much of each ingredient must be used? Okay, so we'll talk units of ingredient 1, units of ingredient 2, units of ingredient 3, and those are the variables that we're going to be solving for. So let's introduce our variables. Let's say let x be the number of units of ingredient 1. And then in a similar way, we can use y and z to be the number of units of ingredients 2 and 3. Okay, now each equation is going to come from one of the nutrients that we're interested in. So we're going to have an equation about vitamin A, we're going to have an equation about vitamin C, and we're going to have an equation about calcium. So we'll just think about each of those equations individually. So I'm just going to recopy a little bit of the table so that we can see what's going on here. So we had vitamin A information in the first row, and then we had our different ingredients. I'll just say 1, 2, 3 across the top here. And then we had milligrams. They were 10, 30, and 20 were the first row. Okay, so if we think about how much vitamin A in total we would be getting from this combination of different ingredients, we'd say, well, if X is the number of units of ingredient 1, and then we multiply that by 10 milligrams per unit, then overall we're getting 10x milligrams just from ingredient 1. And then we're going to add that to 30y is the number of milligrams of vitamin A from ingredient 2. And then we go plus 20z. That's our milligrams of vitamin A from ingredient 3. So altogether, that's our milligrams of vitamin A. And then we were told in the question what we're trying to achieve. So I'm just scrolling back to the question for a second, and we can see in the problem, we were told the combination that we're trying to design. So we're trying to achieve 170 milligrams of vitamin A, etc. So we would like this sum here to equal 170 milligrams. So we're going to do the same thing for vitamin C and for calcium. Let's see what those equations look like. So for the constants here, we're just pulling out the values from the question. We want to achieve 210 milligrams of vitamin C and 370 milligrams of calcium. And then the coefficients are coming from the rows of the table. So there's our system of equations. So now what we'll do is we'll put this into a matrix and then we'll get it into our REF. And you can check if you put this into our REF that you get the following matrix. So let's solve this system and see if we can find a solution to NASA's problem. So I'm just going to circle the leading ones from each of the rows. And we can see we've got a column here without circles. I'm just going to label our variables here. So Z gets a parameter. Z is going to equal T. And if we start at the top row of this matrix, we're saying X minus Z equals negative 22. In other words, if we bring the Z over to the other side, X equals negative 22 plus T. If we do the same thing for Y, we get Y plus Z equals 13. Or in other words, just solving for Y equals 13 minus T. So there we have a solution in terms of our parameter. Now, because this is a real-world problem, we need X, Y, and Z to be non-negative. And that's something that we hadn't really considered before when we were just abstractly solving systems without a real-world context. But now we need to make sure that we're not asking for a negative number or negative number of units of a certain ingredient. Okay, so let's look at our different variables. If we want Z to be non-negative, that's like saying we want T to be greater than or equal to 0. From the X value, we can say, well, we need negative 22 plus T to be greater than or equal to 0. If we do a little bit of algebra here, that implies that T needs to be at least 22. And in a similar way, if we do the restriction for Y, we're saying we need 13 minus T to be at least 0. If we add T to both sides, that implies 13 needs to be at least T. Or often we'll write that inequality just the other way around. That says the same thing as T can be at most 13. So when we say we need these to be true, we're really saying we need this to be true, we need this to be true, and we need this to be true. Well, we cannot find a T value that is at most 13 and at the same time at least 22. So there is no non-negative solution. So we cannot give NASA a solution to the problem. Time for problem 3. We are going to balance this chemical equation. So I'm going to recopy the equation. We've got ammonia plus O2 goes to dinitrogen plus H2O. Okay, what we're going to do is we're going to introduce some variables here. So what we're interested in is how many molecules of each of these substances do we need to balance this equation. So we're going to let W be the number of molecules of ammonia. We'll let X be the number of molecules of O2. Similarly, we can use Y and Z for number of molecules of the other substances. So W, X, Y, and Z are the variables that we're going to be trying to solve for. Now, where our equations are going to come from are the 3 different types of elements. So we're going to have an equation for nitrogen, we're going to have an equation for hydrogen, and we'll have another equation for oxygen. So let's look at nitrogen first. We're just going to think, how many atoms of nitrogen do we have on the left side? Well, the ammonia molecule has 1 nitrogen atom, so that's going to be just W. And we want that to equal the number of atoms of nitrogen on the right side. Well, on the right side, the dinitrogen, the N2, has 2 nitrogen atoms, so that's going to be 2y. So that's what our nitrogen equation looks like. We can do the same thing for hydrogen and oxygen. So for hydrogen, we would have 3w equals 2z. Okay, and then finally the oxygen equation, we would have 2x equals z. So those are the three equations that we're going to be putting into our system. And it's more natural to have these written so that you got all the variables over on the left. So let's just do a rewrite for each of these. Let's say the first equation becomes w minus 2y equals 0. Then we've got 3w minus 2z equals 0 and 2x minus z equals 0. So that's our system of equations, and let's put that into a matrix. So we're going to have three equations, four variables, and let's put that into our REF. So I'll write down our REF and you can check this if you like. So if we circle the leading non-zero entries from each row, there we go. Z is going to get a parameter. So we'll say Z equal T, and let's solve for W, X, Y in terms of T. So our first equation says W minus 2/3 of Z is equal to 0. We actually solve for W. That says W equals 2/3 T. And in a similar way, we can get X equal 1/2 T just by using the second row, and by using the third row of the matrix, Y equals 1/3 T. So there are infinitely many solutions to a system like this. What we want is the smallest non-negative integer solution. So when we say smallest, we just mean we want those coefficients to be as small as possible. Non-negative, because we definitely don't want a negative number of any of those molecules. Integer, because we don't want to take half a molecule, for example. And so what's going to be involved here is just figuring out what T value is going to work. So let's look at the different denominators. We've got denominator 3 and denominator 2. So least common multiple of those denominators would be 6, and that's the T value that we want to use. So we'll use T equals 6. Let's figure out what that means for W, X, Y, and Z. So subbing in T equals 6, we get W equal 4, X equal 3, Y equal 2, and Z equals 6. So I'll just write the answer right down at the bottom here. These are the coefficients for the different molecules in the reaction. So it's 4 ammonia plus 3 O2 gives 2 dinitrogen plus 6 H2O. And there we have a balanced equation. So let's take a look at question 4. The downtown core of Gotham City consists of one-way streets, and the traffic flow has been measured at each intersection. For the city block shown in the figure below, the numbers represent the average number of vehicles per minute that are entering or leaving the intersections during business hours. So for example, if we look just at intersection A, which is right here, you can see you've got on average 10 plus 10 vehicles entering that intersection. So 20 vehicles entering on average, and the number that are leaving, F1 plus F2. So that's the setup. Now there are three things that we're going to do here. Part A, we're going to set up and solve a system of equations to find the values of F1 to F4. And then once we've done that, then a couple other short questions in reference to that. So the governing principle in this problem is that inflow equals outflow at each intersection. And that's just like saying once a car enters the intersection, it has to leave. So we're assuming that no cars are staying parked in the intersection. So based on that, we're going to be able to look systematically at the 4 different intersections in the picture. They were called A, B, C, D. And we'll be able to get an equation just based on the fact that inflow equals outflow. All right, so let's set up our equations. So we're going to have 20 equals F1 plus F2 for intersection A. For B, we said it's going to be F1 plus F3 equals 25. For C, we've got 30 coming in, and that's going to equal F3 plus F4. And then for D coming in, we have F2 plus F4, and that's going to equal a total of 25. So we're going to put this into a matrix, and then we will put that matrix into our REF. So if you like, you can check that the RREF comes out as follows. And let's go about solving this. So we'll just circle the first non-zero entry in each row. You can see that the last column is going to get a parameter. So F4 will be T, and then we can solve for the other F's in terms of T. So top equation will say F1 minus F4 equals -5. We just solve this for F1. F1 equals -5 plus T. And let's do a similar thing for F2 and F3. So F2 will be 25 minus T, and F3 will be 30 minus T. So I've just scrolled back to the question. We've got that at the top of the screen so that we can see what we're going to be doing here. So for part B, traffic is regulated so that F4 takes on a specific value. We want to figure out what will the average flows on the other streets be. So meaning just sub in F4 equal 10, solve for the other Fs. And in part C, what are the minimum and maximum possible flows on each street? So we'll take a look at that. That's basically going to come down to the fact that we want all of our flows to be non-negative. And that's going to force certain T values. So I think I'll do part B over here. So just subbing in F4 equal 10, we'll figure out what that implies for F1, F2, and F3. So F1 will be 5, F2 will be 15, and F3 will be 20. So the point we're trying to get at here is that if you force a value for any of these flows, that then forces specific values for all the other flows. And then part C, I think, is the most interesting one. We need all of these flows to be non-negative. So F1, F2, F3, F4, all must be greater than or equal to 0. So let's figure out what T values are allowable, and then that will lead us to the minimum and maximum flow through each intersection. So we're just going to systematically go through these different F values and figure out what non-negativity forces. So for F1, if we want -5 plus T to be greater than or equal to 0, we could rearrange that to say T has to be at least 5. So I think I'll just keep a list over on the right side here of all these values as we figure them out. For F2, 25 minus T has to be greater than or equal to 0. So if you add T to both sides, that says 25 is at least T. Or if you say that the other way around, that's like saying 25, or T is at most 25. It's just a different way of saying that. T is at most 25. In a similar way, for F3, if you say 30 minus T is at least 0, that implies 30 is at least T. Or if you say that the other way around, that's T is at most 30. So I'm going to add that to the list. And we also have the restriction that F4 is non-negative. So T itself also has to be at least 0. So logically, what we're saying here is that if F1 through F4 are all non-negative, that implies that T has to be at least 5, T has to be at most 25, T has to be at most 30, and T has to be at least 0. So what we're going to do is just essentially take the intersection of all of these restrictions. So once you say that T is at least 5, the fact that T is at least 0 is irrelevant. T being at least 5 covers both scenarios. And similarly, once you say T is at most 25, that makes sure that T is at most 30 is also satisfied. So in order to satisfy all of these, what we need is for T to be somewhere between 5 and 25. So those are the allowable T values to make sure that all these flows are non-negative. And to find the minimum and maximum flows through each intersection, what we're going to do is look back at part A, where we had our solution, and we're just going to see what happens as we sub in these T values. So I'll write down our answer right at the bottom of the screen here. So let's think about F1 first. If we sub in T equal 5, we get 0. And if we sub in t equal 25, we get 20. So that tells us f1 is ranging between 0 and 20. For f2, when we sub in t equal 5, we get 20. And when we sub in t equal 25, we get 0. So again, f2 is running between 0 and 20. So f2 can take on any values between 0 and 20, depending on what the value of t is. Okay, and then let's try f3. Subbing in t equal 5, we get 25, and subbing in 25, we get 5. So that tells us as t varies, f3 is going to be somewhere between 5 and 25. And then finally for f4, because f4 is t, as we run through the t values 5 to 25, f4 can be between 5 and 25. So there we have our solution to part C, where we've described what values each flow can take on. So very last problem, number 5, we're going to find all possible combinations of 20 coins. We're considering the coins to be nickels, dimes, and quarters. That will make exactly $3. So first thing we should do is introduce variables. If the variables are not given in the problem, then quite important to introduce variables at the beginning so that you've got a language to talk about the problem in. So let's say let x be the number of nickels, and we're also going to have dimes and quarters. So we might as well use y and z for those variables. And we've got two conditions or two restrictions that were given in the problem. There was a condition on the number of coins, and there was a condition on the total value, which was we wanted the value of the coins to sum up to $3. So let's talk number of coins. Okay, well, x is the number of nickels. So if we add the number of nickels plus the number of dimes plus the number of quarters, we should be getting 20. That's what we were told in the problem. And then there was the condition on the value. So it's your choice whether you do this in dollars or cents. If you do it in cents, the advantage is you won't have decimals. So you could say you've got 300 cents in total. Each nickel represents 5 cents. So your number of cents is 5 times however many nickels you have. That's just coming from the nickels. Then we add 10y for the value of the dimes and 25z for the value of the quarters. So that gives us our total value, which is 300. So that's our system. And as usual, we'll put that into a matrix and then get it into our REF. So there's our system in matrix form, and you can check that if we put this into our REF, it comes out looking like this. So let's go ahead and solve this. Circle the first non-zero entry in each row. And so z is going to get a parameter here. From the top row, we can say x minus 3z is equal to negative 20. So if we solve for x, that's x equals 3t minus 20. And in a similar way, y will be, you could say 40 minus 4t. Now, if we were just solving a system without any real-world context, this would be our answer. But anytime we're dealing with a real-world phenomenon, we need to think, are there any restrictions? Typically something like our variables should not be negative. So in this case, because we're talking about a number of coins, we definitely don't want to end up with a negative number of coins. So the only real restriction we have to say here is that we need x, y, and z to be non-negative. So let's systematically go through our variables and just figure out what t values would be allowed. So from z, we would say t has to be greater than or equal to 0. From x, we would say 3t minus 20 has to be at least 0. If we do a little bit of algebra, that means 3t has to be at least 20, which means t has to be at least 20 over 3. And because t is an integer value in this context, that really forces t to be at least 7. So you can just check t equals 6 does not quite satisfy that. T equals 7 or bigger does satisfy that. So I'm just going to condense this a little bit and say from the second variable, we need t to be at least 7. And then there will be one more condition from y. So from y, if we have 40 minus 4t, being at least 0. Let's add 4t to both sides. That implies 40 is at least 4t. Or you can write this the other way around. 4t is at most 40, and then divide by 10. So t is at most 10. So highlighted here, we've got the 3 restrictions on the t values. And what we want to do is take the intersection of these restrictions. So for example, if you look at t at least 0 and t at least 7, t at least 7 covers both of those cases. So that's the intersection of those two. And we also need t to be at most 10. So taking the intersection of the 3 tells us that t has to be somewhere between 7 and 10. So just erasing all this side work, what you would write down in your solution is just this restriction on the t values. So you just write that sort of at the bottom of your solution here. T can be anything between 7 and 10, and that ensures that all our variables will be non-negative. So what that tells us is that there are really 4 different combinations of coins that will work. One combination when t equals 7, you can work out what that combo is. Another for t equal 8, 9, and 10. So 4 different possible combinations in total. So that's the end of our applications of linear systems. Thanks for watching.